Okay, guys. Now we're gonna jump into section 6.2. It's line intervals. You can see your learning objectives there, your definitions. We're going to go through some solutions. Sorry, I'm still struggling with this terrible cough. I don't know when it's gonna finally leave me alone. Probably never. All right. Finding the value of a line interval. Find the value of the interval where C is the upper half of the unit circle. So the integrand is two. The figure that I'm going to show you shows the graph of there you go, curve C, and the sheet formed by them. Notice that this sheet is the same area as a rectangle. So this sheet is the same area as a rectangle with I and length 2. Therefore, oh man, I wrote that so big and there's still some stuff that I didn't see I have to tell you. To see this part in action, using the definition of the interval, we let R of T be the parameterization of C. Then and F R T I Z T equals 2 for any number t sub I in the domain of R. So therefore, the limit as n approaches infinity, summation I equals 1 to n, delta Si. So it's going to be the limit summation I equals 1, sorry. Oh, wow, that's so hard for me to draw down there. 2 delta SI. So then we pull the 2 out. And that's going to be 2 times the length of C, which is just 2 pi. All right, and then you'll see the visual. Okay. I believe the next slide is going to be maybe some notes. Those some book notes. Oh yeah, theorems. Oops. Not what I wanted to do. I do that. All right, so take a minute to write those down. Okay, guys. Evaluating a line integral. Find the value of the integral where C is part of the helix parameterized by the following. Parameterized, wow. It's like 9:30 at night. Having a hard time with these words. To compute a scalar line integral, we start by converting the variable of integration from arc length s to t. Then we can use the equation 6.8 to compute the integral. Note that f r of t is cosine squared t plus sine squared t plus t. So that's 1 plus t. And then the square root x prime t squared plus y prime t squared plus z prime t squared. It's gonna be the square root of negative sine squared cosine. And that will get you to the square root of 2. So therefore, C equals 0 to 2 pi 1 plus t square root of 2 dt. Notice that equation 6.8 translates the original difficult line integral into a manageable single variable integral. So this is using then we would have 0 to 2 pi 1 plus t square root of 2 dt. That's going to be square root of 2 t plus square root of 2 t squared over 2 0 to 2 pi. So then the last line you would basically have would be rewriting it. Okay. Independence. Find the value of the interval where C is part of the helix by the following. Notice that this function and curve are the same as in the previous example. The only difference is that the curve has been whatevered so that time runs twice as fast. Okay. So as in the previous example, we would use equation 6.8 to get us to be within one variable of just t. So that starts us out with f r of t would be cosine squared t plus, 2t. Plus sine squared 2t plus 2t would be the same as 1 plus 2t, or 2t. I guess they're switching how they write it, so they're doing 2t plus 1. So then okay, is negative sine of t plus cosine of t plus 4 is equal to 2 square root of 2. So then we have notice that this agrees with the answer in the previous example, changing the double time didn't change anything. as long as the curve is traversed exactly once by the thing. Okay. All right. Moving on to arc lengths. Okay. A wire has a shape that can be modeled with the following. Find the length of the wire. So the length of the wire is given by where C is the curve. So I'm going to go from 0, 4, 5. And now you guys can see why everything was building up to this. All right, so we got this definition you guys need to write down. So it says evaluating a vector line, find the value where C is a semicircle, and there's the information for it. So we're going to use equation 6.9 to convert the variable from S to T. Okay. So here's what we know. So then that tells us R prime of T and that means right. Why is this doing this? Thank you. Okay. Halfway through. Doing great. Okay. So reversing orientation. Find the integral. Notice that this is the same problem as 6.18. Okay. Except that the orientation of the curve has been traversed. In this example, R0 equals -1, 0, and ends at R pi, which is 1, 0. So again, we want to use equation 6.9. Notice that this is the negative of the answer. It makes sense that this is the negative because the orientation of the curve goes against the flow of the vector field. Okay? So, makes sense. Okay. All right. So moving on. Find the value of an integral of the following form. So what we're going to do is, as with our previous examples, we're going to compute this integral. We should perform a change of variables to write everything in terms of t. So we're going to use equation number 6.10. Okay. So here's what we got to do. So that gives us 793 over 15. And then you're going to have a theorem. Almost done, guys. Using properties to compute a vector line integral. Find the value for the following. Note that the curve is the union of its four sides. Each side is smooth. Therefore, C is piecewise smooth. Let C sub 1 represent the side from, so C sub 1 be the side from 0, 0 to 2, 0. C sub 2, excuse me. Okay, so then you have your figure here. Then and that's going to be the summation of all of them. So I'm going to write them, but you might have to squeeze in the rest. All right. We want to compute each of the four integrals on the right-hand side using equation 6.8. For all of them. Before doing this, we need to parametrization of each side of the rectangle. Here are the four parameters. So it's basically just trying to find a way to write this. T to 0 is going to be 0 t to 2. That's for C1. It's going to be 2 t. It's going to be 0 t 1. And it's going to be 2 minus t 1 that's going to be 0 t to 2. And then the last one's going to be 0 to 1 minus t. And it's going to be 0 to 1. Okay. So now that you have all that, let's put it together. You'll get zero to 2. And then 0 to 2. Okay. So notice that the value of the integral is positive, which should not be surprising. As we move along curve 1 from left to right, our movement flows in the general direction of the vector field itself. At any point along C1, the tangent vector to the curve and the corresponding vector in the field form an angle that is less than 90 degrees. Therefore, the tangent vector and the force vector have a positive dot product all along C1. The line integral will have a positive value. So I think I need to add a slide. I believe I do. And then I think the next one has the image. So if I need another one, I think I have half a slide on the next one. All right, the calculations for the three other line integrals are done similarly. So for C2, I know that was there. I think it's just missing, maybe not, because the DR. Okay. Sorry. wanted to make sure I was giving you guys everything you needed. Oh no. Okay. Yeah. No. And then you guys know that the big F's and the big T's are like solidly filled. Let me just check. Oh no. Crap. Ah. Alright, I guess I'll just squeeze it on here. I really thought I had a whole nother half a slide. I did not think that was a whole other problem, guys. Sorry. Alright, let me just try to squeeze the last one in here then. So then if you add everything up, 2, 2, and then so you would get equal to 2. Okay. Let's see. Calculating the mass of a wire. Calculating the mass of a spring in the shape of a curve, given the following information. Calculate the mass of the spring. We must find the value of the scalar integral, line integral of where C is the given helix. To calculate this integral, we will write it in terms of t using equation 6.8. So you're definitely going to have to know those few equations. Okay. So then we have 0, pi over 2, dt plus 4 cosine t sine t square root of 5 tt. Bring the square root of 5 out. E to the t plus 2 sine squared t 0 to pi over 2 sine square root of 5. So that means this problem just proves to you guys that you can have some pretty nasty answers. So don't think that you're wrong just because the answers are gross. Okay. How much work is required to move an object in vector force field along the path? See figure 6.22. Okay. All right. So let's see, to note the given path, we need to find the value of okay. To do this, we use equation 6.9. So we're gonna have I'm sorry, guys, I'm dragging. I'm just super duper late. So this is the proof, I believe, of this. Yes, it is. It says it here, but anyway, take a minute. All right. Super close, super close. Calculate the flux across a unit circle oriented clockwise, and then it gives you the figure. To compute the flux, we first need a parametrization of the unit circle. We can use the standard R of t equal to and 0, 2 pi. The normal vector to a unit circle is cosine t sine t. Normal. Okay, so therefore the flux is okay. Just 2 more questions. Calculating circulation. So, given the following, calculate the circulation of F along C. So we use the standard again, which I just wrote down for you. So then So therefore, the circulation of F along C is going to look like the following. So if you ever wondered what that meant, now you know. Notice that the circulation is positive. The reason for this is that the orientation of C flows with the direction of F. At any point along the circle, the tangent vector of the vector F from F form an angle of less than 90 degrees, and therefore the corresponding dot product is positive. Okay. All right. Last one, calculating work. Calculate the work done on the particle that traverses circle C of radius 2 centered at the origin, orientated by the field. Assume the particle starts its movement at 1, 0. So the work done by F on the particle is the circulation of F along C. So again, we use the following, because I hate that word. And 0, T2, 2 pi, 4, C. So then R prime Okay, so then that also tells us F of R of T so then we have the following. Oops. So ends up being -4 plus 4, which is 0. The force field does 0 work on the particle. Okay. Notice that the circulation of F along C is 0. Furthermore, notice that F is the gradient of the following, I'll add it here. The circulation of F along C is 0. Notice that since F is the gradient of fxy equal to -2x plus y squared divided by 2, F is conservative. We prove in a later section that under broad conditions, the circulation of a conservative vector field along a closed curve is 0. So later, not broad conditions, the circulation of a conservative, nope, that's not that word at all. Conservative vector field along a closed curve is 0. All right, so that is the end of 6.2. We will have regular class, I believe. We will have class. We won't have class tomorrow. We'll have class on the 21st. We won't have it on the 23rd, I believe. All right, I'll see everybody in class. Thank you.